When Xiaomi announced its entry into the automotive industry in 2021, few people took the ambition seriously. The company, best known for producing affordable smartphones and consumer electronics, claimed it would build an electric car capable of challenging the world's most prestigious performance brands. The goal sounded almost absurd. Create a vehicle faster around the Nürburgring than a Porsche, while achieving structural rigidity that could rival some of the most advanced hypercars ever built. Yet what seemed like an unrealistic promise quickly became reality. Just 3 years later, Xiaomi unveiled the SU7 Ultra, a high-performance electric sedan that stunned the automotive world by completing the legendary German circuit in just 6 minutes and 46 seconds, outperforming Porsche's benchmark entries and proving that the company was far more than a newcomer experimenting with cars. What makes the SU7 Ultra truly remarkable isn't only its speed. The real breakthrough lies in how it is built. Rather than following manufacturing practices that have dominated the automotive industry for more than a century, Xiaomi chose to reinvent the process from the ground up. Traditional welding operations, hundreds of stamped components, and massive heat-intensive production stages were largely replaced by an entirely different approach. Using artificial intelligence, the company developed a new high-performance alloy and deployed enormous casting machines, each roughly the size of 2 full-scale sports gyms, to create large structural sections in a single piece. Even the battery was engineered to serve as a core structural element of the vehicle itself. The result is a car whose engineering philosophy feels closer to something from a futuristic concept simulator than a production vehicle. Yet every specification is real, every performance figure has been verified, and every manufacturing system behind it is already operating inside Xiaomi's factories in Beijing. By the end of this video, you'll understand how this technology works and why it is forcing the traditional automotive industry to rethink the future of car production. To understand why this approach is so revolutionary, we need to look at a problem that has existed since the birth of the automobile. Most people never stop to think about how cars are actually built. Surprisingly, the basic manufacturing process used today isn't dramatically different from the one employed decades ago. Large sheets of metal are stamped into shape using enormous presses, and then hundreds of individual parts are welded together to form the vehicle's structure. Imagine assembling a cardboard box. You start with flat pieces, fold them into shape, and join everything together. The method is simple and effective, but every fold introduces a weak point, and every connection becomes another place where problems can eventually develop. As the number of pieces increases, so do the weight, complexity, and manufacturing challenges. Modern vehicles follow the same principle. A typical chassis consists of hundreds of stamped components, connected by hundreds or even thousands of welds. Every connection adds material, increases weight, and introduces another location where vibrations, noise, fatigue, or structural issues can occur over time. For decades, engineers have searched for ways to reduce complexity while making vehicles lighter, stronger, and more efficient. However, the underlying philosophy of assembling large numbers of individual parts has remained largely unchanged. The transition to electric vehicles has made this challenge even more difficult. Unlike conventional cars, EVs must carry massive battery packs, usually mounted beneath the cabin floor. While this improves stability by lowering the center of gravity, it also introduces a significant engineering dilemma. Batteries are extremely heavy, requiring a stronger chassis to support them. The stronger chassis adds more weight, which then demands larger batteries to maintain range. Larger batteries increase weight even further, creating a cycle that becomes increasingly difficult to escape. Tesla was among the first automakers to challenge traditional vehicle manufacturing with a breakthrough technique known as gigacasting. Rather than assembling dozens of smaller metal components through countless welding operations, the company began producing entire sections of a vehicle as a single aluminum casting. The benefits were immediately obvious: fewer parts, lower weight, greater structural rigidity, and significantly faster production. But this innovation exposed a major engineering obstacle that had plagued the industry for decades. The problem wasn't the casting process itself, it was the material. When molten aluminum cools and solidifies, its internal crystalline structure forms in a somewhat chaotic manner. While the resulting component may have the correct shape, its mechanical properties are often insufficient for the extreme stresses experienced by a modern vehicle. To improve strength and durability, manufacturers traditionally rely on heat treatment, a process that reheats the metal in massive industrial furnaces before cooling it under carefully controlled conditions. This additional step strengthens the material by reorganizing its microscopic structure, but it creates a new problem in the process. Heat changes metal. Even the slightest thermal expansion and contraction can cause a large casting to warp, twist, or deform by a few millimeters. For most applications, that may not seem significant. For a vehicle chassis, however, where every mounting point, suspension attachment, and body panel must align with extraordinary precision, even a tiny deviation can become a major issue. A fraction of a millimeter in the wrong place can affect panel gaps. Doors may no longer fit perfectly. Suspension geometry can shift. Components designed to work together with microscopic tolerances suddenly require adjustments and corrections. As a result, automakers found themselves trapped between two undesirable choices: skip the heat treatment and preserve dimensional accuracy, but sacrifice the strength needed for long-term durability and crash performance. Or perform the heat treatment and obtain the necessary structural strength, while accepting that some degree of deformation would inevitably occur. For years, manufacturers searched for a solution. Research teams invested enormous resources trying to overcome the trade-off. Yet despite countless experiments, nobody could fully eliminate the compromise. Eventually, most companies simply adapted their production methods around the limitation and learned to live with it. It became one of those rare engineering problems that many experts quietly began to consider unsolvable. XIAOMI refused to accept that conclusion. When its engineering teams began evaluating existing aluminum alloys, they quickly discovered that none could satisfy all the requirements simultaneously. Some were strong but difficult to manufacture. Others were lightweight but lacked durability. Many still required heat treatment, bringing the same deformation issues back into the equation. The ideal material simply didn't exist. So instead of searching for a better alloy, XIAOMI decided to invent one. The company developed an artificial intelligence platform known as Material Genome, a system specifically designed to accelerate materials science. Rather than relying on years of laboratory testing, the AI could simulate and evaluate millions of potential alloy compositions virtually. Its objective was ambitious but straightforward: create a metal that was strong, lightweight, dimensionally stable, and flexible enough for automotive use while completely eliminating the need for post-casting heat treatment. For human researchers, exploring such a vast design space would have required centuries, if not millennia. The AI accomplished it in a fraction of the time. By analyzing more than 10 million possible alloy combinations and simulating countless variations involving aluminum, silicon, magnesium, rare earth elements, and other additives, the system eventually identified a composition capable of meeting all the required performance targets simultaneously. The result was XIAOMI's proprietary alloy, known as Titan metal. Unlike conventional casting materials, Titan metal emerges from the mold with both its structural integrity and dimensional precision already intact. No additional heat treatment is required. No secondary strengthening process. No risk of thermal warping. The advantages are enormous. Production becomes faster. Energy consumption drops dramatically. Manufacturing costs decrease. Most importantly, the final components maintain extremely tight tolerances, allowing every part of the vehicle to fit together with greater accuracy and consistency. But developing the material was only half the story. A revolutionary alloy is useless without a manufacturing system capable of exploiting its full potential. To make that vision possible, XIAOMI needed something even more extraordinary, one of the most powerful automotive production machines ever built. Tesla's famous gigapress already represented a monumental leap in manufacturing technology. Operating with approximately 9,000 tons of clamping force, it was widely regarded as one of the largest and most advanced casting systems ever installed in an automobile factory. When it debuted, many engineers described it as approaching the practical limits of modern industrial manufacturing. XIAOMI looked at that benchmark and decided to push even further. The company developed its own system, known as the hypercasting machine. Generating more than 9,100 tons of clamping force, this machine is not merely a slightly larger version of existing equipment. It represents an entirely new scale of automotive manufacturing. The system occupies an area roughly equivalent to 2 full-sized basketball courts placed side by side. It weighs more than 1,000 tons and operates under conditions that resemble a metallurgical laboratory more than a traditional automotive assembly line. Titan metal is heated to approximately 700 degrees Celsius before being injected into an ultra-precise mold at tremendous speed and pressure. The process is so fast that air has virtually no opportunity to become trapped inside the molten metal during filling. That detail may sound minor, but it is absolutely critical. Microscopic air pockets inside a casting act like invisible cracks. From the outside, the component may appear flawless. Internally, however, these tiny voids create weak points that can propagate under repeated stress. In a high-performance vehicle capable of extreme acceleration, aggressive cornering, and tremendous structural loads, such defects can eventually become the starting point of fatigue fractures. By minimizing these imperfections, XIAOMI produces castings that are not only lighter and simpler, but also stronger, more consistent, and significantly more reliable than what was previously possible. And that is where the true manufacturing revolution begins. By pushing molten aluminum into the mold at speeds too high for air bubbles to form, XIAOMI creates castings with an internal density typically associated with aerospace-grade components. Every cubic millimeter is packed with material, minimizing voids and imperfections. The result is a level of precision rarely seen in mass-produced automobiles. The rear floor assembly of a vehicle is one of its most critical structural components. In a conventional car, this section consists of 72 individual stamped steel parts connected through approximately 840 weld points. Every one of those components must be manufactured separately, transported, stored, positioned, aligned, secured, and welded into place. This lengthy process requires multiple production stages, extensive equipment, and significant labor. XIAOMI's hypercasting system, however, produces the same entire section as a single integrated component in roughly 100 seconds. 72 parts become one. 840 welds disappear entirely. Hours of assembly are reduced to little more than a minute and a half. The one-piece casting is also about 17% lighter than the traditional multi-part steel structure, while reducing road noise by around 2 decibels thanks to the elimination of gaps, joints, and weld points that can vibrate at highway speeds. The process does not end when the component leaves the mold. Each casting is immediately inspected using X-ray imaging and high-precision laser scanning systems integrated directly into the production line. Before the part even exits the press, artificial intelligence evaluates its structural integrity. If the system identifies any defect, regardless of how small, the component is automatically rejected before a human inspector ever touches it. The level of quality control is effectively beyond human capability. No person could examine every part with such precision at such speed. A new chassis section emerges from the machine approximately every 90 seconds. Yet even this manufacturing breakthrough is not the most remarkable part of the story. XIAOMI's approach to battery design may be even more revolutionary. The real turning point came when XIAOMI stopped viewing the battery as dead weight and began treating it as a structural component. Instead of being merely a heavy energy storage box, the battery became an integral part of the vehicle's architecture. This is the concept behind cell-to-body (CTB) technology. Rather than placing battery cells inside a separate enclosure, XIAOMI integrates them directly into the chassis itself. The upper section of the battery pack serves as the cabin floor, while the cells contribute directly to the vehicle's structural strength. One of the most ingenious aspects of the design is the orientation of the battery cells. In conventional battery packs, safety valves face upward, requiring additional protective structures between the battery and the passenger compartment. XIAOMI reversed this arrangement entirely. By directing the valves downward toward the road surface, the company eliminated the need for several layers of internal protection. The benefits are substantial: less material, lower weight, and an exceptionally slim battery assembly, measuring roughly 120 millimeters in thickness. This lowers the vehicle's center of gravity and significantly enhances stability. The structural gains are equally impressive. The XIAOMI SU7 Ultra achieves approximately 51,000 Nm of torsional rigidity, a figure that comfortably exceeds highly reinforced vehicles such as the Ford F-150 Raptor, which typically falls near 25,000 Nm. In practical terms, this represents a major shift in automotive engineering. The battery is no longer a problem engineers must work around. It has become part of the solution. The chassis is even more rigid than that of a Bugatti Chiron, a car developed by a technology company using its battery pack as a structural backbone, achieves greater rigidity than one of the most expensive road cars ever built. And that rigidity is far more than a headline statistic. It is the foundation that allows every other system in the vehicle to perform at its best. When the chassis remains stable under load, the suspension operates exactly as intended. Dampers respond precisely according to their calibration. Tires maintain optimal contact with the road surface, even during aggressive cornering. The vehicle behaves exactly as its engineers intended, because the platform beneath it remains exceptionally rigid. And that platform was designed to handle 1,148 horsepower, generated by 3 electric motors. Each motor spins at an astonishing 27,200 RPM. That figure represents a production car record for an electric motor. For comparison, many high-performance electric motors operate at roughly 20,000 RPM. XIAOMI's units spin about 35% faster, extracting more power from a package that is both smaller and lighter. These rotational speeds approach the territory of jet turbine technology. Without the titanium-reinforced chassis, the CTB battery structure, and the integrated engineering philosophy behind them, the forces generated by this level of power would place enormous stress on a conventional vehicle over time. Instead, XIAOMI developed the material, manufacturing process, chassis architecture, and battery integration as parts of a single unified system. Every element was engineered to support the others, creating a structure where the whole is greater than the sum of its parts. This is what truly makes the SU7 Ultra significant. XIAOMI did not simply build an impressive electric car. The company demonstrated that starting from a blank sheet of paper, without accepting decades-old assumptions about how vehicles must be designed, can unlock entirely new possibilities in automotive engineering. Using artificial intelligence to create an entirely new alloy, rather than merely improving existing materials, changes the game from the very beginning. Building the world's largest die casting machine and using it to replace dozens of individual components with a single structural piece transforms how automobiles are manufactured. Integrating battery cells directly into the chassis and turning them into a load-bearing part of the vehicle fundamentally redefines what a car is. The XIAOMI Vision GT concept, with its theoretical 900 horsepower and aerodynamic characteristics so extreme they would likely be prohibited in Formula One, is not a distant vision of the future. It is a glimpse of what becomes possible when all of these technologies converge into a single engineering philosophy. More importantly, the foundations of that philosophy already exist today inside XIAOMI's manufacturing facilities in Beijing. The hypercasting system is already producing massive chassis sections every 90 seconds. The cell-to-body architecture is already powering vehicles in the hands of real customers. These are not laboratory experiments, concept sketches, or ambitious promises. They are production technologies operating at scale right now. What makes this development truly significant is that its implications extend far beyond the success of a single company. It represents a wake-up call for the entire automotive industry. For more than a century, vehicles have largely been built using the same basic principles. Hundreds of stamped metal components welded together piece by piece, with the battery treated as a separate component that engineers must accommodate within the structure. That model is now being challenged by a radically different approach. In this new paradigm, materials, manufacturing equipment, structural engineering, software, and energy storage are conceived as parts of a single interconnected system from the very first design stage. Artificial intelligence is used not simply as a tool for optimization, but as a way to explore solutions that human engineers might never have considered on their own. The result is not an evolution of the traditional automobile. It is a complete rethinking of how vehicles are designed, built, and integrated. That is why manufacturers around the world are paying close attention. The question is no longer whether these technologies work. The question is how quickly the rest of the industry can adapt. And perhaps an even bigger question remains. If a company that was primarily known for smartphones and consumer electronics was able to enter one of the most complex industries on Earth and produce a vehicle that competes with established automotive giants, what happens when other technology companies attempt the same feat? Could Apple do it? Could Samsung? Could Google? More importantly, could they start from a blank sheet of paper and build something that challenges not only traditional automakers, but the very assumptions on which the modern automobile has been built for generations? What do you think? Could another technology giant replicate what XIAOMI has accomplished and create a world-class vehicle from scratch? Leave your thoughts below and let's discuss it.